For billions of years, the cosmos has been illuminated by the incandescent glow of countless stars, beacons of creation that forge the very elements essential for life. Their brilliance fuels galaxies, warming planets, and painting the darkness with vibrant light, a vast celestial tapestry that defines our observable universe. Yet despite their apparent eternal majesty, every star, regardless of its size or luminosity, is a temporary phenomenon. Each one follows an inevitable life cycle, born from collapsing gas, burning through its nuclear fuel, and ultimately facing its own extinction, gradually fading into the cosmic night. Our Sun, a typical yellow dwarf star, has sustained life on Earth for over 4.5 billion years, its steady fusion providing warmth and light. But even our familiar star is middle-aged, destined to eventually exhaust its internal hydrogen fuel, marking the beginning of its transformation. Understanding the demise of stars is not merely a theoretical exercise, it's a journey into the deep future of the universe itself. As these cosmic furnaces wink out, the very fabric of reality transforms, leading to an epoch of darkness unlike anything we can currently comprehend. To grasp this ultimate fading, we first must comprehend the lives these giants lead. Stars are born within vast clouds of gas and dust, called nebulae, where gravity pulls matter inward, causing it to collapse and heat up, eventually igniting nuclear fusion in their cores. This fusion process, primarily converting hydrogen into helium, releases immense amounts of energy, creating an outward pressure that precisely counterbalances gravity's inward pull. This delicate equilibrium defines a star's main sequence lifetime, its longest and most stable phase. The duration of a star's main sequence life is primarily dictated by its mass. Massive stars, despite having more fuel, burn through it at incredibly rapid rates, living fast and dying young, often lasting only a few million years. Conversely, smaller, less massive stars, like red dwarfs, consume their fuel at an exceptionally leisurely pace. They are the marathon runners of the cosmos, potentially enduring for trillions of years, long after larger stars have met their end. As stars exhaust the hydrogen in their core, the delicate balance shifts. Gravity begins to win, the core contracts and heats up further, igniting helium fusion in a shell surrounding the core. This signals the star's departure from the main sequence. For stars like our Sun, this process leads to a dramatic expansion, transforming them into red giants. The outer layers swell enormously, becoming cooler and redder, potentially engulfing inner planets as they grow to immense sizes. The red giant phase is a relatively brief interlude, just a few 100 million years. For a star of the Sun's mass, helium fusion will then begin in the core, further extending its life, but this too will eventually cease. Once helium fusion stops, the core of a Sun-like star contracts no further. Instead, its outer layers gently drift away into space, forming a glowing shell of gas known as a planetary nebula, one of the most aesthetically beautiful stellar remnants. At the center of this expanding nebula lies the star's cooling core, a white dwarf. This incredibly dense object, roughly the size of Earth but with the mass of the Sun, is composed primarily of carbon and oxygen left over from fusion. White dwarfs no longer undergo nuclear fusion, they are essentially stellar embers. Their luminosity comes solely from the residual heat from their past life, which slowly radiates away into the cold vacuum of space, a process spanning eons. Over truly immense timescales, far longer than the current age of the universe, these white dwarfs will continue to cool. As they lose their remaining heat, their light will dim, shifting from white to yellow, then reddish, and finally fading entirely. The theoretical ultimate fate of a white dwarf is a black dwarf, a cold, dark, inert lump of degenerate matter. However, the universe isn't old enough for any black dwarfs to have formed yet, making them purely hypothetical objects. Now consider the fate of truly massive stars, those born with more than 8 to 10 times the mass of our Sun. Their lives are far more dramatic, culminating in explosive events that reverberate across galaxies and seed the universe with heavy elements. These behemoths fuse heavier and heavier elements in their cores, progressing from hydrogen to helium, then carbon, oxygen, neon, magnesium, and silicon, building up an onion-like structure of concentric shells of different fusing elements. This process continues until the star's core is primarily iron. Iron fusion does not release energy, instead, it consumes it. At this critical point, the core collapses catastrophically, triggering one of the most violent events in the cosmos. The collapse is so rapid and powerful that it rebounds, sending a tremendous shockwave outward through the star's layers. This cataclysmic explosion is known as a supernova, briefly outshining entire galaxies. What remains after a supernova depends on the original mass of the star's core. For stars with sufficiently large cores, the remnant can be a neutron star, an incredibly dense object packed with almost unimaginable quantities of matter. A typical neutron star is only about 20 kilometers in diameter, yet it contains more mass than our Sun. A single teaspoon of neutron star material would weigh billions of tons, crushingly heavy due to the extreme compression. Neutron stars are also stellar remnants without active fusion. They radiate residual heat and magnetic energy, slowly diminishing their luminosity over billions of years. Some spin rapidly, emitting beams of radio waves as pulsars. As with white dwarfs, neutron stars will eventually cool down, losing their energy to the surrounding vacuum. Over unimaginable timescales, they will become black neutron stars, completely inert and undetectable, cold cosmic ashes. But the most extreme stellar demise occurs when the original star's core is even more massive, typically greater than 3 times the mass of our Sun after the supernova. In these instances, not even neutron degeneracy pressure can halt the collapse. The core continues to collapse endlessly, forming an object of infinite density, a singularity enshrouded by a boundary from which nothing, not even light, can escape, a black hole. Black holes are not holes in space, but rather regions of spacetime where gravity is so overwhelmingly strong that it warps the very fabric of the universe around them. They are the ultimate cosmic traps. In our current epoch, black holes grow primarily by accreting matter from their surroundings or by merging with other black holes. This is how supermassive black holes at the centers of galaxies grow to billions of solar masses. But in the incredibly distant future, when the stellar nurseries have long since faded and nearly all available gas has been locked into dead stars or black holes, the universe's energy landscape will be drastically different. The future of stars isn't just about their individual deaths. It's about a cascading series of events that will transform the cosmos from a vibrant, light-filled realm into an unimaginable expanse of cold, dark emptiness. As billions upon billions of years pass, the white dwarfs, those cooling stellar embers, will continue their slow descent into darkness. Their final glow, a relic of their fiery past, will dissipate into the expanding void. The process of a white dwarf fully cooling into a theoretical black dwarf takes astronomical amounts of time, requiring perhaps a Google years, a one followed by 100 zeros, timescales far beyond anything we can truly grasp. Even the largest white dwarfs, those that might have been closer to the Chandrasekhar limit, will eventually succumb to this cosmic chill. Their once brilliant cores will become solid, crystalline carbon, a diamond the size of a planet, but utterly frozen. The universe's mass budget will increasingly shift from luminous matter to these dark, compact objects. White dwarfs, neutron stars, and black holes will be the primary residents, silent witnesses to a cosmic future devoid of light-emitting stars. Our Milky Way galaxy, currently a magnificent spiral, will one day be a graveyard of these stellar corpses. Gravitational encounters will shuffle these dead entities, occasionally flinging them into the intergalactic void. Meanwhile, the red dwarfs, the smallest and most numerous stars, are expected to endure for trillions of years. Their sluggish fuel consumption means they could outlive every other type of star, becoming the last stellar lights in the universe. But even red dwarfs are not immortal. Eventually, their entire mass is consumed by fusion, slowly transitioning to helium. Without the core shell structure of larger stars, they will simply dim and cool off. The ultimate end for a red dwarf is a blue dwarf, then a white dwarf, and finally a black dwarf. This sequence will unfold over timescales so vast that they are almost incomprehensible, stretching for hundreds of trillions of years. As the last red dwarfs exhaust their fuel and become black dwarfs, the era of normal stellar activity, the stelliferous era, will finally come to an end. The universe will enter a new, profoundly different phase. The degenerate era. In this degenerate era, roughly 1014 to 1040 years from now, the universe will be dominated by white dwarfs, neutron stars, and black holes, along with a scattering of planets and asteroids that have escaped their stellar hosts. During this era, very little new energy will be produced. The cosmos will primarily be a theater of cooling and decay, where the last vestiges of thermal energy slowly dissipate into the expanding void. Planets once warmed by their suns will become wanderers, unbound frozen spheres adrift in the immense darkness between dead stars. Their surfaces, if they exist, will be plunged into eternal night and temperatures near absolute zero. Occasional gravitational interactions might see a black dwarf collide with another, generating a brief flash of light, a fleeting mimicry of the stellar brilliance of a bygone age. But these events would be exceedingly rare. The very structure of galaxies will gradually dissolve. Stars and stellar remnants, which orbit a common galactic center, will be slowly ejected due to gravitational encounters, becoming intergalactic nomads. Over timescales of around 1019 to 1020 years, the vast majority of stellar remnants within galaxies will be flung out into the desolate cosmological background, leaving behind mostly central, supermassive black holes. The universe will become increasingly sparse, with vast, empty stretches of space separating the few remaining concentrations of matter. The cosmic web, once illuminated by galaxies, will fray and disintegrate into isolated islands of darkness. In this extreme future, even the very atoms that constitute matter are not necessarily stable. A hypothetical process, proton decay, suggests that protons, the building blocks of atomic nuclei, might themselves spontaneously decay over stupendous timescales. If proton decay occurs, with a predicted half-life of at least 1034 years, then over incredibly vast periods, all normal matter, planets, dead stars, dust, would slowly dissipate into fundamental particles like positrons and photons. This means that even the cold, dark black dwarfs and neutron stars, the ultimate remnants of stellar evolution, would eventually cease to exist as coherent objects, dissolving into a diffuse soup of elemental energy. Such an event would transform the universe into a truly featureless void, where matter as we understand it simply would not exist. There would be no solids, no liquids, no gases, only a dilute gas of fundamental particles. However, the existence of proton decay is still a theoretical prediction, untested by experiment. If protons are truly stable, then matter would persist, locked within the dense remnants, though still isolated and cold. Regardless of proton decay, the true ultimate masters of the final cosmic epochs are black holes. They are the longest-lived objects known, but even they are not eternal. Through a quantum mechanical process discovered by Stephen Hawking, black holes slowly evaporate by emitting what is known as Hawking radiation. This process is incredibly slow, especially for supermassive black holes. The rate of Hawking radiation is inversely proportional to a black hole's mass. Smaller black holes evaporate faster, while supermassive ones take an incomprehensibly long time, perhaps 1067 years for a solar mass black hole and up to 10100 years for the largest. These timescales are so immense that they make the age of the universe seem utterly insignificant. When the last black hole evaporates, nothing will remain of the star-forming universe's primary gravitational wells. The universe will then enter the dark era or black hole era, spanning from 1040 years until approximately 10100 years. During this time, black holes will be the primary source of entropy, radiating away their mass. After the last black hole has evaporated, the universe will consist only of a very dilute gas of photons, neutrinos, electrons, and positrons, spread out over an ever-increasing volume. This final state is often referred to as the Big Freeze or heat death. It is a state of maximum entropy where all energy is uniformly distributed and no further thermodynamic processes, no work, no life can ever occur. No stars will shine, no galaxies will coalesce, no new structures will form. The very concept of time, as driven by change and events, might well lose its meaning in this ultimate, unchanging cosmic silence. The universe approaches a state of ultimate rest, a cold, dark, infinitely dilute soup of fundamental particles, endlessly expanding into an even colder, darker, and emptier void. This is the universe's final, irreversible destiny. Reaching these unfathomable timescales, where the universe's light has been extinguished and its matter dissipated, allows us to reflect on the nature of reality itself. Is this the true ultimate fate, or are there hidden possibilities? Current cosmological models strongly favor the Big Freeze scenario, given the observed accelerated expansion of the universe driven by dark energy. This continuous expansion cools and dilutes everything. However, some alternative theories propose different ultimate fates. The Big Crunch, where expansion reverses into a collapse, seems less likely given current data, but remains a fascinating cosmic possibility. Even more speculative is the Big Rip, where dark energy's influence grows so strong it literally tears apart everything, from galaxies to atoms, ultimately shredding spacetime itself. But based on current understanding, the universe's ultimate fate appears to be one of cold, dark emptiness, a slow, inevitable march towards thermal equilibrium where no processes are possible. This cosmic narrative, from fiery birth to ultimate dissipation, underscores the transient nature of even the most immense and powerful objects in the cosmos. Nothing, it seems, truly lasts forever. The sheer scale of these future epochs highlights how incredibly young we are in the universe's lifespan. Our entire history is but a fleeting blink in the cosmic calendar, a mere fraction of a second. The fleeting existence of stars, planets, and life itself within this grand cosmic drama suggests a preciousness to the present moment, a unique window of opportunity for complexity and sentience. The knowledge of this ultimate cosmic night does not diminish the wonder of the daytime. Instead, it amplifies the profound privilege of living in an era when the lights are still on, when the universe is still vibrant. The elements forged in ancient stars, scattered by supernovae, are the very atoms that constitute our bodies and our world. We are literally stardust, a momentary assembly of cosmic material. Our existence is possible only because stars lived and died, producing the carbon, oxygen, and other heavy elements necessary for complex chemistry. Without stellar deaths, there would be no life. The fading lights of stars, therefore, are not just a story of cosmic demise, but also a story of cosmic recycling and renewal, albeit on a grand scale that far transcends individual lives or even species. As we look up at the night sky, we are observing sunlight that took mere minutes to reach us, and starlight that traveled for years, centuries, or even millennia across the galaxy to greet our eyes. Each photon that strikes our retina carries with it a story of nuclear fusion, of a star's struggle against gravity, a tiny messenger from cosmic titans, some of whom may have long since faded. The light we see tonight comes from stars still actively burning. The light from a white dwarf that vanished an eon ago, or a black hole that evaporated untold eons from now, would be beyond our perception. This journey into the distant cosmic future reminds us of the profound indifference of the universe to the fleeting existence of life. Yet, it is within this indifference that our moments of consciousness gain meaning. The awareness of universal entropy, the drive towards ultimate disorder and equilibrium, is a humbling realization. It places our endeavors, our civilizations, and our very existence in a vast and unique cosmic context. Could any future civilization find ways to prolong the cosmic light, to manipulate stellar remnants, or even black holes to extract energy beyond their natural lifetimes? Such concepts border on the fantastical now. The engineering required to harness the energy of evaporating black holes, or to somehow reignite dying white dwarfs, would demand technologies far beyond our current comprehension, defying even the laws of thermodynamics as we understand them. Perhaps, in a universe on the verge of ultimate darkness, the only sources of light will be artificial, powered by the last vestiges of matter or the faint energy of Hawking radiation, meticulously conserved. Such a future paints a bleak picture, a universe where the ultimate triumph lies not in creation, but in the conservation and slow release of the universe's final, dwindling reserves of energy. Even if life could persist in these unimaginably cold and dark conditions, its form would have to be radically different. Not carbon-based beings, but perhaps silicon-based, or even something entirely non-corporeal. The informational content of the universe itself will degrade. Black holes are the ultimate information sinks, and Hawking radiation, while returning energy, disperses the information that formed the black hole. The cosmos, in its final state, might be a place where there is simply nothing left to know. The stars that illuminated the paths of light, the galaxies that mapped matter's distribution, will be gone. This profound end state, the heat death, is not a cataclysmic event, but rather a gradual, inexorable fading into silence and uniformity, a triumph of disorder over structure. The very expansion of the universe, currently accelerating, means that even stray photons from other galaxies will eventually be stretched to infinitely long wavelengths, rendering them undetectable. This means our observable universe will shrink dramatically over cosmic time, ultimately encompassing only our local group of galaxies, which themselves will eventually merge into one supergalaxy. But this supergalaxy will also eventually disintegrate, flinging its components into the intergalactic void, further contributing to the ultimate isolation and emptiness. The universe's journey begins with a fiery bang, followed by a period of stellar brilliance, and concludes with a whimper of endless cold and darkness. It is a solitary journey towards ultimate cosmic equilibrium. The tale of the fading lights is thus a cosmic saga of profound transformation. From the first stars igniting the darkness to the last black hole sighing its final Hawking radiation, it's a story of ultimate change. During these long eons of cosmic decay, even the tightest gravitational bounds will weaken. Clusters of galaxies, once magnificent and bright, will slowly drift apart over truly immense timescales. The voids between superclusters will grow to incomprehensible sizes, the expansion of space itself stretching any remaining photons to pointlessness and any matter to extreme dilution. Consider the energy budget. Initially, the universe contained immense energy locked in hot plasma and matter. As stars formed, this energy was released as light. Now, it's dissipating as low-grade heat. The second law of thermodynamics dictates that entropy, or disorder, in a closed system always increases. The universe, if considered a closed system, is marching inexorably toward maximum entropy. This means that all forms of usable energy, will eventually be converted into unusable, uniformly distributed thermal energy, rendering any kind of work or organized process impossible. The initial inhomogeneities of the early universe, the slight variations in density that allowed stars and galaxies to form, will be smoothed out into a monotonous, featureless state. Even the cosmic microwave background, the remnant radiation from the Big Bang, will be stretched and cooled to temperatures indistinguishable from absolute zero, vanishing into the background noise. The very concept of temperature as a measure of atomic motion might lose its meaning when the universe cools to near absolute zero and particles are so far apart they rarely interact. What happens to information in such a future? If all matter decays and black holes evaporate, does the universe retain a memory of its past, or is it utterly erased? The information paradox in black holes, whether information is truly lost or subtly encoded in Hawking radiation, remains a profound question, hinting at the depths of quantum gravity we yet don't understand. If information is truly lost, then the universe faces an information death alongside its heat death, where no record of its magnificent history remains. Total amnesia. Consider the philosophical implications. Does a universe without conscious observers even exist in any meaningful way if there's no one left to witness it or interpret its processes? The incredible unlikeliness of life emerging in the first place, coupled with the vastness of cosmic timescales, makes our brief, conscious moment even more extraordinary. The Big Rip scenario offers a more dramatic, less tranquil end, where the accelerating expansion continues to increase, ultimately overcoming all fundamental forces. First, galaxies would be torn apart, then stars from their planetary systems, then planets themselves. Eventually, even atoms would be ripped into their constituent particles, and eventually, the particles themselves. This would be an end not of cooling silence, but of violent, unimaginable fragmentation, a universe ending not with a whimper, but a final, deafening tear. The Big Crunch alternative, if gravity were to eventually overcome dark energy, would see the universe collapse back upon itself, reversing the expansion. Stars and galaxies would rush back together, space would contract, and temperatures would rise again, culminating in a superheated, infinitely dense singularity, perhaps sparking a new Big Bang. This cyclical, oscillating universe model, while elegant, faces challenges from current observations of cosmic acceleration, suggesting expansion will continue indefinitely. Regardless of the ultimate mechanism, the era of luminous stars, as we know them, is a temporary phase in the universe's unimaginably long timeline. We are in its youthful, vibrant prime. The eventual dominance of degenerate matter, white dwarfs, neutron stars, and black holes, represents a cosmic turning point from creation of light to the slow decay of its remnants. The ultimate fate of any surviving particles in the very far future, whether protons decay or not, would be to drift in extraordinary isolation, rarely interacting, if ever. Conceive of a single electron, billions upon billions of light-years from its nearest neighbor, moving at almost imperceptible speeds. That would be the universe's ultimate resident. The energy density would drop to near zero, approaching the vacuum state. The universe would be indistinguishable from true nothingness, except for the lingering presence of these widely scattered fundamental particles. This final state offers no solace for life, no hope for complex structures or continued evolution. It is the ultimate cosmic dead end, a timeless, placid, empty uniformity. Yet even in this bleak outlook, there is grandeur. The universe's fundamental laws, its inexorable march towards entropy, are themselves a testament to an underlying, unchanging reality. The fading lights remind us that we live in a special time, a brief moment when the conditions are just right for complexity, for starlight, and for us to look up and ponder it all. This is the cosmic dawn of awareness, where a universe slowly dying can reflect upon its own existence, an extraordinary paradox of consciousness in a fading cosmos. The journey from the Big Bang to the Big Freeze is a testament to the power of gravity, the dance of nuclear forces, and the ultimate victory of thermodynamics. The stars will go out, not with a sudden bang, but with an unimaginably slow, fading whisper. The light that defines our cosmos is finite, and its eventual absence is the universe's most profound future. As the universe ages beyond even the cooling of all white dwarfs into black dwarfs, gravitational interactions will become the dominant force on what little remains. Over timescales of around 1034 years, random gravitational encounters between black dwarfs will occasionally scatter some of them into the immense emptiness of intergalactic space. Even bound multi-star systems, those that survived the stellar deaths, will gradually be broken apart by the slow, inexorable gravitational dance and the accumulated effect of countless weak interactions. The galaxies, already emptied of their luminous stars, will continue to dissolve internally. The central supermassive black holes will reign over increasingly sparse collections of dark remnants. At this stage, the dominant objects will be the supermassive black holes at the centers of what were once galaxies. They represent the largest accumulations of mass that will endure for the longest time. These behemoths will continue to grow, albeit very slowly, by occasionally accreting the stray particles or the few remaining stellar remnants that happen to drift too close over trillions of years. But this growth is ephemeral in the face of their ultimate fate, Hawking radiation. The universe will enter the black hole era, where these massive entities are the only significant structures left. The evaporation of a supermassive black hole that is 1 billion times the mass of our Sun would take an estimated 100 years, a number so vast it challenges human comprehension. When the last supermassive black hole finally evaporates, it will release a final burst of low-energy photons, a cosmic sigh marking the very last significant event in the universe's history. After this epoch, the universe will be a cold, empty void, sparsely populated by non-interacting fundamental particles like photons, neutrinos, electrons, and positrons. If proton decay occurs, then even the electrons and positrons will eventually annihilate each other, turning into photons, leaving only a sea of photons and neutrinos. These photons will be stretched to incredibly long wavelengths by the universe's accelerating expansion, becoming indistinguishable from the background, their energy virtually zero. The cosmic microwave background, already stretched to radio waves, will eventually be so diffuse and cold that its photons are too rare and too low energy to ever interact. The effective temperature of the universe will continually approach absolute zero, causing all atomic and subatomic motion to cease or become incredibly rare. In such a state, there would be no thermodynamic gradient, no hot spots or cold spots, nowhere for energy to flow, thus rendering any kind of work or organized activity physically impossible. This is the ultimate triumph of entropy, the maximum state of disorder and thermal equilibrium. The universe has reached its final resting place, a state of cosmic quiescence. The universe, once a crucible of creation and a canvas of light, becomes a vast, empty mausoleum, a testament to the finite nature of energy and the inexorable march of physics. What happens to space itself? The expansion continues, stretching metrics, creating more volume, but without anything to fill it, it becomes an even emptier expanse. The light from our own Milky Way, even if it was somehow still shining, would take longer than the age of the universe to reach even relatively nearby galaxies due to expansion. This means the universe, from any given point, becomes progressively isolated. The concept of an observable universe would dwindle to nothingness as everything recedes beyond any horizon. The universe doesn't disappear. It simply becomes boring, utterly devoid of change, structure, or interaction, a uniform sea of low-energy particles. This ultimate cosmic loneliness, with particles separated by distances that preclude any interaction, paints a picture of extreme, cold isolation on the grandest scale. The very concept of time, as a measure of change, becomes meaningless in a universe where nothing happens, where all processes have ceased. Could there be a rebound after the heat death? Some esoteric theories suggest quantum fluctuations might one day, in an unimaginably distant future, create a new Big Bang. This eternal inflation, or multiverse, hypothesis implies our universe is but one bubble among an infinite sea of others, perpetually spawning new universes from a quantum foam. In such a scenario, the ending of our universe would simply be a local event within a grander, eternal metacosmos, a rebirth of sorts for an infinite succession of realities. However, these remain theoretical constructions, far removed from testable physics. For now, the most scientifically robust prediction for our universe is the cold, silent end. The fading lights. It is the story of stars, galactic structures, and ultimately matter and energy bowing to the laws of entropy. It is the universe's final, irreversible act. But in this ending, there is a profound beauty. The beauty of fundamental laws, the elegance of physical processes, and the quiet dignity of a cosmos completing its journey. The stars will go out, one by one, until the universe is nothing but a cold, dark, infinitely dilute void. This is the ultimate fate that awaits the lights of our cosmos. This journey through cosmic time, from a hot, dense singularity to a cold, empty void, paints a sobering picture of our universe's finite life and ultimate destiny. Within this vast narrative, our entire cosmic history, the formation of galaxies, the birth of stars, the emergence of life, is but a fleeting, luminous moment. Yet this very finiteness amplifies the preciousness of our epoch, a temporary window where thermodynamic gradients allow for complexity, consciousness, and the appreciation of the cosmos. The stars, those magnificent cosmic furnaces, are the universe's great alchemists, forging the heavy elements necessary for planets, chemistry, and eventually, life itself. Their eventual demise, whether as white dwarfs, neutron stars, or black holes, is not just an ending, but a necessary step in the grand cosmic cycle of matter and energy. The cooling of stellar remnants, the slow, agonizing evaporation of black holes, and the hypothetical decay of matter itself represent increasingly profound stages of cosmic dissolution. Each stage is characterized by diminishing energy, increasing entropy, and the gradual loss of structure, leading towards a universe that becomes ever more uniform and featureless. The sheer timescales involved, the googles of years, challenge our intuitive grasp of duration, making our human history seem infinitesimally brief. The vacuum of space, already vast, will expand to encompass distances so astronomical that light itself, if it were still produced, could not bridge the gaps. This ultimate isolation means no two particles will ever find each other again, no complex structures will spontaneously form, and no new information will ever be created. The universe, once a symphony of light and matter, will become an infinite, silent abyss, its history lost to the vastness of time and space. Yet despite this cold, dark future, the act of contemplating it, of understanding our place within this grand cosmic cycle, is a uniquely human triumph. Our ability to trace the destiny of stars, to project billions of years into the future, speaks to the immense power of scientific inquiry and human curiosity. We inhabit a universe that permits the existence of conscious beings, even if only for a cosmic blink, to witness its brilliance and contemplate its ultimate fading. The fading lights are not merely a scientific prediction, but a profound philosophical contemplation, inviting us to ponder purpose in a universe seemingly devoid of ultimate meaning. Perhaps the meaning lies not in the destination, the cold, dark end, but in the journey itself, the brief, blazing era of stars, life, and consciousness within this immense expanse. The universe's ultimate fate ensures that every moment, every photon, every interaction between particles is a unique and unrepeatable event in the grand cosmic tapestry. So let us cherish the light, the warmth, and the vibrant complexity of our universe, for these are transient gifts in the grand scheme of cosmic time. The story of the fading lights is the universe's most enduring tale, a silent, majestic narrative written in the slow decay of stars and the relentless march of entropy. It's a reminder that even the most colossal and seemingly permanent phenomena in existence are locked within the finite embrace of time and the universal laws of physics. And so we bid farewell to the brilliant show of stars, understanding that their eventual silence is not an end to wonder, but the ultimate profound chapter in the grand cosmic drama that contains us all.